Anthony, did you ever have to program a turtle robot when you were learning to program?
I've never programmed a turtle robot, no.
Okay. So I had to do this when I was learning Java. And in robotics, the concept of a turtle bot is often that you have some kind of robot who can move across the screen. And it has some kind of pen, so it has some trace. So you can start programming, go upward or go forward by 1 meter, then turn right by 90 degrees, go forward by 1 meter, turn right by 90 degrees. So that way you trace a pen over a virtual canvas.
The logo language was based on that, right?
Yeah, indeed. So the history is that the computer scientist Seymour Papert, who created the programming language Logo in 1967, apparently they used this programming language. So these are things I didn't know, to direct like a big robot with a pen in the middle, which would let you make drawings on actual paper.
Okay.
It's pretty cool,
Instead
right?
of a plotter, a printer.
So apparently in 1967, people learned to program with a physical moving plotter. Like they immediately start with a robot.
That's pretty cool.
Yeah, instead of using a virtual canvas. And that is round and crossed like a turtle. But the other thing I found was that turtle robots, their first mention is in the 1940s. They were invented by Gray Walter. And he was using analog circuits as brains.
Wow.
And his more advanced model could already go back to a docking station when the battery became empty.
That's pretty cool. In the 40s.
In the 1940s, yeah. I will put the video in the show notes. And I will also put 2 articles in the show notes. One is the history of turtle robots. Someone wrote an article about that for Weekly Robotics. And another article on the history of turtle robots as programming paradigms.
Very cool.
Yeah.
Slow and steady.
Yeah, slow and steady. And it's a great way to get started with programming. All right, welcome to Generally AI Season 2, Episode 4. And in this InfoQ podcast, I, Roland Meertens, will be discussing coordinate systems with Anthony Alford.
How's it going, Roland?
Doing well. Do you want to get started with your coordinate system research?
Let's go for it. So I decided to go with an AI theme of coordinates, and perhaps you can guess where I'm going. We'll see.
Tell me more.
Well, in the olden days, a teacher, for example, in a history class, would often ask me and other students to write a paper about some topic. So let's say the topic is the Great Pyramid of Egypt. Now, probably most students don't know everything about the Great Pyramid, and the teacher says, anyway, you have to cite sources. So you can't just write anything you want.
I always hate that part. Yeah, I always say, I found this on the internet. These people can't lie.
Well, I'm talking about the days before the internet, but the 20th century, let's say, we would go to the library, an actual physical building, and there would be a big drawer full of small cards, the card catalog.
Yeah.
These are in alphabetical order, and so we'd scroll through till we get to the P's, and then PY Pyramid, Great Pyramid of Egypt, right?
Yeah.
This card has a number on it. This is the call number for books that are about the Great Pyramid of Egypt.
Yeah.
So in the US, a lot of libraries use a catalog system called the Dewey Decimal System for nonfiction books.
Okay.
It's a hierarchic classification system. So books about history and geography in general, they have a call number in the range from 900 to 999.
Yeah.
Within that, books about ancient history are in the range of 930 to 939.
Yeah.
Books about ancient Egypt specifically have call numbers that begin with the number 932. And then depending on what ancient Egyptian topic, there will be further numbers after the decimal point.
And maybe a weird question, but were you allowed to go through these cards yourself, or did you ask someone else where can I find information about ancient Egypt?
Both methods do work. If you're young and adventurous, perhaps you'll go to the card catalog and start rifling through. But yes, in fact, a lot of libraries had a person whose job was to answer questions like that. the reference librarian.
Yeah, because I'm too young. I never saw these cards. My librarians would already have a computer they would use to search.
Right. But the point there is that the card catalog is pretty familiar to us in, speaking of search, the card catalog is an index.
Yeah.
And it maps those keywords like Great Pyramid of Egypt. It maps those keywords to a call number or to maybe multiple call numbers. Actually, university libraries, in my experience in the US, they don't use Dewey Decimal. They use a different classification, but the idea is the same. Anyway, it's a hierarchy and it assigns a call number to each book. So to go actually get the physical book, it's hopefully on a shelf that's in a cabinet. We call these stacks. That's the lingo.
Yeah.
So the classification hierarchy is itself mapped physically to these stacks. There will be a row of cabinets for the books that are in the 900 to 999 range. There may be one cabinet for the 930 to 939, and there may be one shelf for 932, and so on. Now that I think of it, this structure is itself somewhat like a pyramid.
Perfect example.
Hopefully, if nobody's messed with them, the physical order of the books matches the numeric order. So you're doing an index scan or index search, if we're thinking about it, in terms of a database or information retrieval, because that's what this is.
Yeah.
Right? It's literally information. Okay.
Yeah, and it's good that it's indexed by topic, because otherwise you don't know if you're searching for P for pyramids or G for Great Pyramids or E for Egyptian Great Pyramids.
Right. And you might try all, like if you're not talking to the reference librarian, you might try all those keyword searches in the index.
Yeah.
So now that I've got a couple of books, I can use that content in those books to help me produce my essay about the Great Pyramid. Now, that was the bad old days of the 20th century. Here in the 21st century, it's like you said, you do an internet search, or maybe you read Wikipedia.
Yeah.
That's just the first quarter of the 21st century. Now we're into the second quarter of the 21st century, and we're in a golden age of AI. We don't have to even do that. We just go to ChatGPT and like copy and paste the assignment from the syllabus webpage as a prompt. And ChatGPT writes the essay.
Quite nice. Quite neat.
Well, in theory. So there's a couple of problems. First, the teacher said, cite your sources.
Yeah.
And, you have to do that like in the content where maybe you quote something or reference, you need to put it in there. The other thing is ChatGPT is good, but maybe it's not always 100% historically accurate.
Yeah, it sometimes makes up things.
And it really only knows things that are in its training data, which is large, but maybe there's some really good books or papers that are not on the internet that might not be in that training data. So I think what is the answer.
Are we going to retrieve some data before we're processing it?
Yes, it is RAG time. So the key technology now is retrieval augmented generation, also known as RAG, R-A-G. So the general idea, we know that if we give an LLM some text, like the content of a history book, LLMs are quite good at answering questions or creating summaries of that content, that you include that with your prompt. Now, ignore the problem of limited context length, which is a problem. The other problem is, how do you know what content to provide it?
Yeah, you can't give it the entire stack of books.
Exactly. And even if you had the content electronically, you had picked it out, you want to automate this, right? You don't want to have to go hunt down the content to give to the LLM. So finding the right history book, the right content in an electronic database of content. Well, we already said it. This is information retrieval. And, again, in the old days, we'd use natural intelligence. We would use the reference librarian or go look up some keywords in the card catalog.
It is too bad that the librarian is not very scalable.
Exactly right. We want to automate this and scale it. So let's take an analogy. The key idea of RAG is take your LLM prompt and automatically assign it a call number. So now you can go directly from your prompt, your instructions for writing the essay, Now we have automatically assigned it a call number. And now you just go get those books automatically and add that with your prompt.
Sounds pretty good.
Yeah, more precisely, we have an encoder that can map an arbitrary blob of text into a point in some vector space, with the requirement that points that are near each other in this space represent texts that have similar meanings. So typically we call this an embedding. So we take an encoder, we apply the encoder to the prompt that turns that into a vector. Then we have all of our books in the universe. We have encoders applied to them, and we get vectors for them. We find the vectors that are close to the vector for our prompt. So easy peasy, right?
Easy peasy.
Right. Well, here's the problem. So the encoder
encoding your data.
Well, there's that. Well, like I'm just going to assume somebody encoded all the books in the library. Okay. That's a one-time job. The problem is that people usually use BERT as the encoder. Well, the embedding vector that you get is 768 dimensions. And so the question is, what does it mean to be nearby something in a 768 dimensional space?
Yeah, that depends on what distance function you want to use.
That's exactly right. With call numbers, it was easy because they're scalars. So the distance function is subtract.
Oh, it's quite interesting. I never even realized that core numbers could be subtracted.
Well, that's how you do it, right? If you go to find your book 932.35, you probably don't do a scan. You probably do like some kind of bisecting search, or you need to go over to the 900s, and then you jump to the middle of the 900s and scan back and forth depending on the number that you're at.
Yeah, and also for the library, it of course makes sense that they put books which are similar close together.
Yeah, well, you physically store them in order of their call number.
Yeah.
More or less. So, but anyway, like you said, this distance is the closer they are to zero, like the closer the two call numbers are together, physically the books are closer together. So anyway, we need a distance function, or the opposite of a distance function, which is a similarity, right? The smaller the distance, the more similar. In the case of these embeddings, people typically use a similarity measure called cosine similarity.
Yeah.
Now, if you've ever worked with vectors, you probably remember the inner product, or sometimes called the dot product. To explain this without a whiteboard, let's say we're in 3D space. So each vector has X, Y, and Z. The dot product of two vectors is you take the X from the first one, multiply by the X from the second one. Then you do that for the two Y components and then the two Z components. You add those all up. That's the dot product. And that's a single number, a scalar.
Yeah.
The geometric interpretation of the dot product is it's the length of the first one times the length of the second, and then times the cosine of the angle between them.
Yeah.
So you could divide the dot product by the length of the two vectors, and what you're left with is the cosine of the angle. And if they're pointing in the same direction, that means the angle is 0 and the cosine is 1. If they point in the opposite directions, the cosine is -1. And in between there, if it's 0, they're at right angles.
Yeah, intuitively, you always think that it doesn't really matter what the magnitude of the interest is, as long as the interests are at least in the same direction, it's probably fine in your library.
Yeah, and I'm going to explain why. Anyway, the cosine similarity is a number between -1 and +1. And the closer that is to +1, the nearer the two embeddings are for our purposes. And you may wonder why cosine similarity? So again, with 3D space, X, Y, and Z, there's a distance called the Euclidean distance, which is our normal, like the distance between 2 points is a straight line, right?
Yeah.
So you basically take the square of the X's, the square of the Y's, the square of the Z's, add them up and take the square root. So
as long as we are in a Euclidean space, that's the case.
And in vector terms, that's just the magnitude of the vector drawn between those 2 points. Well, if you wonder why you don't use that, why instead you use cosine similarity, if you look on Wikipedia, it's something called the curse of dimensionality. Basically, when you have these really high dimension spaces, and if the points are uniformly spread around there, they actually aren't. Like the middle of the space and the corners of the space are empty-ish. And most of the points are actually concentrated near the surface of a sphere in the space. So when all the points are on a sphere, their magnitudes are more or less all the same. And so you don't care about them. And so the thing that makes them different points is they're at different angles. They're at different angles relative to some reference. So that means we don't care about the magnitude of vectors in the space. We care about the direction. And that's why cosine similarity.
Is there any reason that the magnitude of the vectors tends to be the same?
It's just the way that these sparse high dimensional spaces, it's just the math that they work out.
Okay.
And in fact, because the magnitudes are all more or less the same, or at least you can take a shortcut. You can just use the dot product. You don't have to get the cosine similarity. You can just do the dot product. That's a nice shortcut because GPUs are very good at calculating dot products.
Yeah.
And so let's back up, right? We take our prompt, we encode it. We've already encoded the content of all the library. We just find the vectors in the library that have the largest dot product with our prompts vector. And in the original RAG paper, they did that. It's called maximum inner product search. So basically, you take your queries vector, you do the dot product with the vector of all the documents and take the ones that have the biggest.
Yeah.
What's the problem now? I bet you know.
What is the problem?
Well, the problem is you have to basically, every time you have a new prompt, you have to go and calculate the dot product against every other document.
Yeah, if only there was a better way to store your data.
Well, there's a better way to search, it turns out.
Yeah.
The default way is linear complexity. So for a small library, maybe no big deal. But, if we're talking about every book ever written, well, if you compare it with index search in a database, that's complexity around log n.
Yeah.
So linear is way worse. It's terrible.
Yeah.
So again, it turns out this is a well-studied problem, and it's called nearest neighbor search.
Yeah. Approximate nearest neighbors or exact nearest neighbors?
Well, one is a subset of the other. So if you go back to the database search, that's log n. And you can actually use a tree structure for nearest neighbor search. You can use something called a space partitioning tree and use a branch and bound algorithm. And with this strategy, you're not guaranteed log n, but the average complexity is log n. But this usually works better in a lower dimensional space.
Okay. So why is it on average? Do you keep searching or?
Well, I think it's just you're not guaranteed, but based on the statistics, you can mathematically show that on average, you get a log n complexity. But remember your favorite algorithm?
My favorite algorithm.
What was your favorite algorithm?
Hyperlog.
Right. So approximate, you already said it, approximate nearest neighbor. When you want to do things at scale, you approximate. So it turns out that a lot of RAG applications use an approximate nearest neighbor search, or ANN, which also stands for artificial neural network, but just a coincidence. So there are several algorithms for ANN, and they have different trade-offs between speed and quality and memory usage. Now, quality here is some kind of metric like recall. Yeah. So with information retrieval, you want to get a high recall, which means that of all the relevant results that exist, your query gives you a high percentage of those.
Yeah. One
of the popular algorithms lately for ANN called Hierarchical Navigable Small World, or HNSW. HNSW is a graph-based approach that's used in a lot of vector databases. I actually wrote an InfoQ news piece about Spotify's ANN library, which uses HNSW.
Oh, is it Voyager?
That's correct, yes.
Yeah.
Hey, you must have read it.
Oh, I tried it. It's pretty cool.
Oh, okay. Well, you know all about this stuff.
Oh, I love vector searching.
So I found a nice tutorial about HNSW, which we'll put in the show notes, and it expressed a very nice definition. It's concise. Small world referring to a unique graph with low average shortest path length and a high clustering coefficient. Navigable referring to the search complexity of the subgraphs, which achieve logarithmic scaling using a decentralized greedy search algorithm. And hierarchical, referring to stacked subgraphs of exponentially decaying density. So, all of this to find out who is my neighbor.
Who is your neighbor and in which space are they your neighbor?
Yeah. So I think I've filled up my context window for today. And for homework, I will let our listeners work out analogies between this topic and library stacks and pyramids.
Yeah, for library stacks, I'm just hearing that they could have multiple boxes with the stacks and you just move from box to box, from room to room.
So here's a very interesting thing. Here in my hometown, there's a university, North Carolina State University. Their engineering library has a robot that will go and get books out of the stacks.
Oh.
It's basically an XYZ robot.
Yeah.
And it'll move around and get books out of the stacks for you.
Oh, nice. That's pretty cool.
Yeah, it looks really cool. Always
adding an extra dimension, then you can represent way more knowledge.
So that's my fun fact.
That's a pretty good fun fact.
Hey folks, have you ever wondered how software leaders pushing the boundaries in today's environment are adopting emerging trends? At QCon San Francisco, November 18 to 22, you will step inside the minds of the engineers who will share how they implement innovations in real-world scenarios. Explore tracks like architectures you've always wondered about, engineering productivity, and, my favorite, generative AI in production and advancements. Here you can learn from practicing senior software developers on how they are adopting emerging trends. Find out more about the conference at QConSF.com. We hope to see you there.
All right. For my fun fact for today, as the topic is coordinate systems, for software, there's many ways to represent a map and location software, right? So this can be important for your user data, maybe for helping with people and finding like where they are, finding interesting locations close by. And the most popular format here is WGS84. But what I wanted to dive into is the history of coordinate systems, especially how different countries chose them and some of the legacy systems which are still in place. Because the history of coordinate systems is, of course, longer than just computers. People wanted to know who owned what land for quite a long time. People wanted to know how to get somewhere for quite a long time. And first of all, there's different ways to project a map, right? So you want to have a map in 2D, and our Earth is a sphere. In that way, you can project a sphere onto a cylinder, a cone, or just a flat disk on top of the sphere. And you always get some kind of compromise. So you can choose to keep the angles of the map accurate. That's, for example, the Mercator projection used by Google Maps. So if you're going on Google Maps, you're zooming out, then all the angles are preserved, but the sizes are not very true. One fun question, by the way, maybe you can help me out with this, Anthony, is that I always ask, what is bigger, Greenland or Australia, and by how much?
Oh, well, Australia is quite large. And again, I think the Mercator projection distorts our view of Greenland for those of us who are familiar with it.
Yeah.
So Australia is much larger, but I couldn't tell you like by a factor or whatever.
Yeah. I like to ask this to people because first I ask them what they would estimate, and then I show them the Google Maps projection, and I ask them if they want to change their guess. And sometimes people change it in the wrong direction, even though they know that Mercator doesn't preserve size. Even though they know that the map is lying, they just can't get around the fact that Greenland looks really big on the map. So if you want to fix this, you can use the more wider equal area projection to ensure that all the map areas have the same proportional relationships to areas on the Earth. And the other thing you can do is if you want to, for example, to keep the distance constant, there are equidistant projections that have a correct distance from the center of the map. So this is useful for navigation. For example, if you want to have something centered around the UK, that you at least know if I want to go here, it's equally far as if I want to go here.
Okay.
And here, another fun fact for you is that azimuthal equidistance projection is the one they use for the emblem of United Nations. So, United Nations is this emblem where you see this map from the North Pole. That is an azimuthal equidistance projection where the distance is constant.
Okay, nice.
But as I said, I wanted to talk a bit about order systems in the world and which projection they picked and perhaps some of the technical depth and incredibly smart choices they made when doing so. And first off, in the UK, they have the Ordnance survey maps. It's basically the national mapping agency for Great Britain. And in a previous episode of Generally AI, I already told you about multiple telescopes in the observatory in Greenwich, right?
Right. Yeah.
And I think I also told you that they have multiple telescopes, which all have a different prime meridian line, which indicates 0 or used to indicate 0. I discovered that the Ordnance survey meridian was picked in 1801, which is 50 years before this newer prime meridian was released.
Oh.
And nowadays, with a GPS, the prime meridian moved again. But the Ordnance survey maps are basically 2 prime meridian switches away from what it used to be.
I don't know, but I'm guessing from the name that they would, in worst case scenario, use these maps to choose targets for artillery.
Well,
so hopefully they don't miss.
No, actually, it's what I think is probably a good reason to keep the Ordnance survey maps the same, is that they probably use it to determine whose land belongs to whom.
Sure.
So you want to be able to keep measuring in the old way as you already determined who owns what land.
Makes sense.
Otherwise, but we will see this later in this episode, you start publishing error maps like the Netherlands is doing. But yeah, it's interesting that since 1801, when they picked this survey meridian, they were for a long time simply 6 meters to the east of what people started to call 0 for a long time. I can also imagine that this is still confusing nowadays if people use their own GPS device and compare it to some old document from the 1800s and discover that their place is very much far away from where they thought it should be. But yeah, I'll post an article to this Ordnance Survey 0 Meridian in the show notes.
Okay.
Anyways, moving to a different country. In the Netherlands, the Geographic Information System, the GIS system, is called Rijksdriehoekscoördinaten. So it's the National Triangle Coordinate System.
Okay.
And as you can already guess, this mapping is accurate in angles.
Ah, okay.
And Wikipedia says it approaches being accurate in the distances. So it's not accurate in distances.
Oh, I see. And so I guess it's basically you need to orient in the right direction, but the distance is approximate? Is that?
Well, so the thing is that if you have these coordinates, the angles between your coordinates are the same as the angles in the real world.
Oh, cosine distance.
Yeah. So the coordinates are in kilometers and then meters, right? It's just that 1 meter in coordinates or like 1 kilometer in coordinates isn't a kilometer in the real world. So 1 kilometer on the map in coordinates isn't necessarily 1 kilometer in the real world. So the center of the map is a church in Amersfoort, so basically in the center of the Netherlands. Around there, the scale is 10 centimeters per kilometer too small.
Interesting.
Yeah, I mean, it's not a big error. It's just only 10 centimeters.
You know, this reminds me again of the last season where the king found out that his land was smaller than the map said it was.
Yeah, so if you would take the Dutch triangle coordinate system and then determine that you're going to walk 10 kilometers in the center of the Netherlands, you would have walked 1 meter too little after walking 10 kilometers.
Would you even notice though, right?
Indeed, you probably wouldn't. On the edges, so if you go towards the coast areas into Germany, it's 18 centimeters per kilometer too large.
Oh, so you could wind up in Germany and not know it. Or would you know it? You might know.
You will find out that you're crossing the border because it says you're crossing a border.
Well, wait, Schengen. You guys are all...
Yeah.
You just walk, right?
Yeah, you can, from where my parents live, you can very easily cycle to Germany. But yeah, it's interesting that because you have such a small country, you can project things in a flat way. And then
the country's rather flat as well, I believe.
The country is rather flat as well. Yeah, indeed. I will get to the height of the Netherlands, actually, because that's also interesting. Because they use different landmarks than the landmarks used for the triangle coordinate system.
Okay.
So as I said, for the triangle coordinate system, the center of the coordinate system, let me tell you a fun fact about that first. So that's a church in Amersfoort. And if you look at the coordinates, so there's an X and Y component where X goes from west to east and Y goes from south to north. That's relatively simple. But the X coordinates are between 0 and 280 kilometers. The Y coordinates in the Netherlands are between 300 and 625. So 0.00 is basically somewhere to the north of Paris. And the nice trick here, which I think is just genius, is that all the coordinates in the Netherlands are positive, and the Y coordinates in the Netherlands are always larger than the X coordinates.
Interesting.
Unlike continental Netherlands. So this removes all the possible confusion around what coordinate. So if I give you two coordinates, I don't even have to tell you this is X, this is Y.
Got it.
I can turn them around, I can flip them around. Because as software engineer, whenever it says coordinates, you get two numbers. I always plot like latitude, longitude, like try all these combinations to make sure that everything is correct. And here in the Netherlands, if only people would use the national triangle coordinate system, there would be no confusion in your software.
Is that a thing that most Netherlanders are aware of?
Probably not. I must also say that this coordinate system is not used a lot, probably mostly for people who are doing navigation challenges or like scouting or something. Although I must say that it is quite nice to take one of those maps because they are divided in a very nice way. It's very clear how far everything is, because with latitude and longitude, the distance between one latitude or one longitude is different depending on where you are on Earth, right?
Yes, but there's a conversion to nautical miles, but I can't remember it off the top of my head.
That's a good point. I wanted to say in the Netherlands it's fixed, but we just learned that it's 10 centimeters per kilometer too small in the center and 18 centimeters per kilometer too large in the edges.
But, originally part of the development of the metric system was to take the circumference of the Earth and make fractions of it to be the meter originally. I don't think it worked out.
I think there's also a map system where they try to keep the patches the same area, but then you get problems when you want to move from patch to patch. Mm-hmm. So if you have coordinates or if you have a route which crosses multiple patches, one point on one patch doesn't necessarily map to the same place on another patch.
It's a tough problem.
Yeah, and that's why I like to talk about it. It's a lot of technical depth, and it becomes more difficult once you start doing things with software or self-driving cars or things like that. In terms of technical depth, the original map of the Netherlands was made between 1896 and 1926. And as you can imagine, we now have way more accurate mapping tools.
Right.
But I already alluded to the fact that if you already mapped out a place and you say, this is your property, you can't really say, oh, there's a new coordinate system, let's go measure everything again and assign this again. So what they do in the Netherlands, I think on 3 different occasions, they published a correction grid with corrections up to 25 centimeters. Okay. So you can take an original coordinate and then apply the correction grid to get the coordinates in what is actually measured.
Gotcha. Well, not to derail your talk, but here again in North Carolina, we have a border with another state, South Carolina.
Yeah.
And about 10 years ago, they had to adjust it. Basically, the border had become ambiguous. Like it was unclear where it actually was. And so they fixed it and agreed on where the border is. And there were some people who woke up one morning in a different state without having to move. Yeah.
I can tell you one other fun fact about borders in the Netherlands and between Germany, and that is that in the Netherlands, after World War II, there were some proposals around what part, like, can we maybe have some part of Germany to make up for the Second World War? So they got a few parts of Germany, but those are super small regions, like a village or something. And this wasn't really working out, like taking a long time to move people, make sure everything was working well, build schools, etc. So at some point they gave it back. But then weeks before they were giving back this country, big trucks would already start moving in with loads of goods in them. They would find places in the village to park. And like hours before this transition happened, big trucks would show up with loads of butter inside. So basically, at 12 o'clock at night, the country swapped. And these goods never crossed a border, so they didn't have to pay taxes.
Loophole.
Yeah, so they found a loophole which you could only do one night because some parts changed country overnight.
Interesting.
One last fun fact here about coordinate systems. You already said the Netherlands is quite flat. Good point. But this grid only tells you XY coordinates. And it's mostly based on locations of church towers to measure angles between. So that's quite neat. Those are relatively consistent places. And you can see between them. There's a separate mapping for height above sea level. The new Amsterdam Ordnance datum. And this is actually used in a lot of Western European countries. And these points are indicated by screws on specific buildings. And I know this because once in high school, we had to make an accurate map of a field close to our school. And I was tasked to propagate the height from this screw to the rest of the field.
Wow.
We actually had these systems they use in professional area measuring setups.
The surveying tools, transit.
There was something where something was perfectly flat, and then we would stand somewhere with like a height meter, measure the difference in height, place the measuring device somewhere else, have the person with the height meter stand somewhere else. Mm-hmm. We also had to do it twice because the first time we made a mistake. I don't know anymore what we did, but it's just teenagers trying to come up with a way to measure a field.
Very cool.
All right. Words of wisdom. Did you learn anything in this podcast, or did you learn anything yourself recently?
The fact that all the points in a high dimensional space are on a sphere was new to me. Maybe not all, but the fact that they all more or less have similar magnitude. That was an interesting fact that I was not aware of.
You would say that means that there is space in the high dimensional space left over. The place in the middle and the corners could be utilized to store more information.
One would think, but then that would mess up the assumption of the cosine distance.
Yeah, but more space to store. It's free. It's free storage.
Just add another dimension.
Yeah. That's why I always throw all my stuff on the floor in my room. I pay for it. I can store it wherever I want, everywhere in the space.
Definitely.
One thing from my side in terms of learning things, one recommendation I want to give you is, have you heard of the post office scandal in the UK?
No, tell me.
It's quite interesting. So the post office in the UK adopted a bookkeeping system by Fujitsu called Horizon. And it was basically plagued with bugs. So sometimes the system would duplicate transactions. Sometimes it would change some balance when users would press enter at some frozen screen multiple times. So you're like, oh, it's frozen. Let me press enter. Every time like something happened with your balance. And it was possible to remotely log into these systems. So Fujitsu or Horizon could remotely change the balances on these systems without the postmasters knowing. And I learned last week that rather than acknowledging these bugs, these postmasters were sued for the shortfalls of the system, because the system would say, you owe us £30,000.
Oh, wow.
Yeah, and so these postmasters were prosecuted, got criminal convictions, and this is still going on and still not fully resolved today.
That's terrible.
It is absolutely insane. So I watched this drama series called Mr. Bates versus the Post Office, and I can definitely recommend you to watch this because it tells you a lot about impact your software can have on individuals, and to what great length companies are willing to go to hide the impact of bugs or systems like this.
Goodness gracious.
Yeah, it's insane. We can do a whole episode about about the post office scandal, I think.
That would be depressing.
Yeah, but I must say it's very interesting. Like every time when you read on this and you think, surely by now they will acknowledge that there can be problems like this. The post office just doubled down, hired more lawyers, created bigger lawsuits, and absolutely ruined the lives of people who were a sub-postmaster in the last 20 years, actually.
Wow.
As I said, can recommend this as a thing to watch.
Sounds good.
Anyways, talking about recommendations, if you enjoyed this podcast, please like it. Please tell your friends about it. If you want to learn more things about technology, go to InfoQ.com, take a look at our other podcasts, take a look at our articles and the conference talks we recorded. Thank you very much for listening. And thank you very much, Anthony, for joining me again.
Fun time as always.
Fun time as always. Thank you very much.
So long.
Any last fun facts you want to share?
Well, I don't know if we want to put this one on the air, but I was looking at how property is described here in the U.S. in a legal document.
Yeah.
So you may know, you may not, that we have a system called township and range.
Yeah.
And I think it was invented by our president, Thomas Jefferson. After our revolution, we had all this land that, legally speaking, were not owned by anyone.
Yeah.
So they divided it up into a grid. So they laid a grid out over it. So here's a description of a piece of property. Township 4 north, range 12 west.
Yeah.
The south half of the north half of the west half of the northeast quarter of the northeast quarter of the north half of the south half of section 6.
Okay. Yeah. So they made a grid and then they went really, 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 really deep.
Subdividing the grid. Yep.
Yeah. I do like that. When people started mapping this, they were probably like, there's so much land. It doesn't really matter how accurate this is. Probably North US, South US is probably enough.
Well, what's interesting, surveyor was sort of a high status job in the colonial days.
Yeah.
So George Washington was a surveyor.
Yeah.
And Thomas Jefferson amused himself by designing buildings. So these guys took it pretty seriously.
Yeah.
That was the age of the Enlightenment and Renaissance men and all that.
But if you are not good at mapping, you don't come home on your ship.
Yeah, exactly.
And you, if there's no massive road yet, or you don't know where you are, you don't reach the village you wanted to get to.
Exactly.
Yeah, interesting.